Our first idea, a microbial carrier consisting of a vesicle propelled by microbes into the direction of the target. These carriers will transport vesicles containing the protein Cas9 to kill antibiotic-resistant bacteria in fish farms. Antibiotic resistance is currently one of the biggest challenges to the farming sector worldwide. We presented this idea at the Rathenau Institute, which is an institute to stimulate discussions concerning societal aspects of science and technology. They asked us, what about safety if genetically modified organisms are released into the environment, and can the microbial carrier swim against the current? Apparently, our first idea was neither responsible nor relevant, so we went back to the drawing table. Participating in iGEM made us get up to date on all the cutting-edge sensitive machineries in the synthetic biology. We changed Cas9 to the recently discovered Cas13a. In addition, we found an interesting article about tardigrades, which are organisms that can survive in harsh environments such as extreme drought. This, in combination with elements of our old plan, like putting proteins into vesicles, was what we wanted to work with. As non-experts in the antibiotic resistance field, we did not know what the best application for our design could be and which antibiotic resistance to scope on. Considering this, we discussed our ideas with some experts and risk assessors.
First of all, you need to make sure that you're working with an antibiotic producing bacterium. You're not working with a virus, because antibiotics don't work with viruses. So you have to make sure that you very rapidly detect what kind of antibiotic resistance genes you're talking about. The problem is that there's many different types of antibiotic resistance genes for different classes of antibiotics. And it's very tricky to detect all of these variations in one test.
Challenge accepted. A device that will quickly detect whether or not antibiotic is effective against the bacteria causing the disease. This device, however, needs to be safe for the end user and for the environment.
Using a GMO in your device, which you are also going to use outside the lab, is quite difficult because that needs a lot of safety requirements. But you can think of using products of the GMO, and the product is just not a living entity, so it has other safety requirements, and we are all used at using products of GMOs.
The feedback that we received was so crucial to our project that it completely changed the design of our device. Besides adjustments with respect to safety and responsibility, we also aim to integrate relevance into our project. With this in mind, we called some stakeholders.
We discovered that the Netherlands actually achieved the top position in combating antibiotic resistance. Integrated human practices became a vital part of our project, as at this point we were unsure how we could consolidate to the top position of the Netherlands.
After looking into different animal diseases, the cow caught our attention, since the dairy industry is an important engine of the Dutch economy. We met with milk farmers and veterinarians to discuss what our device should detect to be relevant. It turned out that mastitis was the most challenging disease with significant economic impact. Mastitis is an udder infection caused by bacteria, where apparently antibiotic resistance is a major problem.
Wij komen er dan achter dat er bijvoorbeeld stukjes in zitten of dikkere melk is. Zodra dit het geval is, beslissen wij of we het eerst preventief gaan behandelen of gelijk antibiotica erin gaan. Wij switchen wel vaak van antibiotica gebruik per jaar tegen mastitis. Dit is natuurlijk ook een gevolg van hoge productiviteit en dan bacteriën in de omgeving.
We met with experts Dick and Vimmer from the Veterinary Research Center in Lelystad to brainstorm about what antibiotic resistance genes would be most relevant to detect. Genes that make mastitis bacteria resistant against multiple drugs seem to be most interesting, not only with regards to mastitis, but antibiotic resistance worldwide.
Other requirements that we also integrated in our design were user-friendliness, storability, fast detection, on-the-spot detection, reliability, sensitivity, accessibility, and cost. To get these values more clear and concrete, we changed our design accordingly. However, this was a challenging process. In the next video, you will see why this was challenging for us as engineers and what we recommend other teams to do to improve this process.